Okay, so let's do some informal review of last week again. I'm probably going to do this most days. And when you guys watch the video, because I'm not here tomorrow morning, by the way, I'm staying with Melissa tomorrow morning. When you guys watch a video of my lesson a couple years ago, I'll do the exact same thing in that video. I think it's important to review these concepts because so far you've learned no, two equations, right? It was like 1 over f equals 1 over do plus 1 over di. And there was like magnification equals some ratios equal to each other. And I hope you guys would agree with me. The math is pretty straightforward. Like literally just plug some numbers in a formula, you're good to go. That's not where you're going to struggle, right? Where you're going to struggle is with your theory, your knowledge, you're wrapping your head around this stuff, right? So even though it's redundant to kind of do this every single class, I think it's worthwhile because we really need to make sure that the basics are definitely there so that you don't have to spend most of your mental processing time trying to rethink through which is a bigger wavelength, radio waves or microwaves. So like you just know that, right? So that you can devote your really really deep thinking space to the harder questions. You know what I'm saying? So start at the beginning. Electromagnetic radiation. For 1 point, what causes it? Yeah, you guys earned a point. Good job, guys. I don't know what our points are worth today. Accelerated charges, right? Now, accelerated charges can happen a couple different ways, right? One of the ways you can have an accelerated charge is basically you have, say, a proton or neutron. No, not a neutron. That wouldn't work. A proton or electron, an alpha particle. And you could have it, say, jump from this side over to this side over here, and literally it goes from having no velocity, and then the spark jumps across, and it has no velocity, and then it has a final velocity. That would have an acceleration, right? That would cause EMR. And we saw that in that Hertz experiment, where he managed to make the first transmitter and receiver. You guys remember that experiment? Okay. But there's another way that you could have EMR get formed as well. Acceleration can happen from a change in velocity, right? Now, a change in velocity could be because the speed itself goes from 0 to 50 or 55 to 12 or whatever the numbers are. But you can also change a velocity by having it change its direction. And so if you ever have a charge that's going around in a circle, for example, that will also give off EMR because that actually is accelerating at that point, right? It's accelerating internally towards the middle. Does that work? So there's the first thing you need to be aware of is this is what causes EMR. So second thing then we should talk about is, well, what really is electromagnetic radiation? And there's two things I want to elaborate on this. First, there's two different models of EMR. There's the wave model, where we consider that it has kind of an amplitude, it has a period, it has like a frequency between how far the crests of the wavelengths happen to be. So it can act like a wave, but we also have evidence that it acts like a particle. And we're going to get into the weird quantum craziness a little bit later in the unit, the idea of like, well, which one is it? Is it a wave? Is it a particle? Is it both? How does it decide which one it is? Well, we'll get to that later. So that's one part of it. The other part of knowing what EMR is just knowing what some of the different things it can do are, depending on where in the spectrum it falls. So usually I start from highest wavelength to lowest wavelength. Why don't we go opposite direction this time? So let's go highest frequency. What's the highest frequency EMR we know about? Yeah, cosmic radiation probably seems to emanate from things like the sun or other sorts of interstellar objects, right? This has such a high frequency and such a short wavelength that it literally phases right through the Earth. We don't even notice it. It's very hard for us to even to detect it. So I know very little bit about cosmic, but that would be the smallest. What's next? Gamma. What do we use gamma for? Give me an example. Say it louder. Yeah, chemotherapy uses gamma radiation. By the way, this just came to mind as I was speaking. I remember a diploma question that I saw where they gave it was multiple. It was like a matching kind of thing where they gave you four like fill in the blanks, and they gave you four uses, and you were supposed to match the use of the EMR to the type of EMR. Does that make sense? So like when we get to the next one up after gamma, there's X-rays. What would we use X-rays for? Medical imaging, something along those lines. All right. So, do you guys know how X-rays are formed? Basically, they take electrons. I believe I need to relook this one up. They take electrons and they fire them at a screen, and they fire them so fast that when they hit the screen, they go from a fairly large velocity to basically no velocity whatsoever because they're like slamming into a brick wall, right? Well, that change in velocity causes an acceleration, right? And the higher the acceleration, perhaps the higher the frequency. That's how they make their X-rays. Does that make sense, right? So even just knowing how they get formed is important. So X-rays are next in terms of your frequency. Then ultraviolet. Yep. And ultraviolet is starting to get to the point. All of these things here we've talked about have a frequency high enough to basically penetrate the human body and cause some sort of internal issues. Right? Like X-rays can cause birth defects. Gamma radiation, I mean, is enough to kill cells that are cancerous, right? Ultraviolet radiation, we know it mostly because of its ability to give you skin cancer and sunburns. Right? So those three on that end of the spectrum are probably more dangerous to the human body. Then you've got your visible light, which going backwards, I guess, in terms of the spectrum, will go violet, indigo, blue, green, yellow, orange, red. Thank you. Whatever Roy G. Biv backwards would be. Wavelength of red light. Go. Nice, 700 watts. Good job. Yeah, it basically ranges between 700 nanometers to about 400 to 450 or so, maybe 300 nanometers for your purple. Good job, though. Yeah, I think that's worth knowing is the rough spectrum there. So, okay. Then after you've got your visible light, you've got your infrared. After infrared, you've got your, which was only chosen because micro is small and it's smaller than. Perfect. And those are kind of your long range waves. Fair enough? Cool. Okay. What speed do all waves travel? Which I think we chose because, I mean, light is part of EMR, but don't forget, if it feels like you're missing a value, that value could be 3 times 10 to the 8. Okay. So basically, that was kind of our main concept of day 1. Those are some of our main pieces. Okay. Day 2, we talked about reflection. And so by virtue of it being a wave or even a particle, it has the ability to bounce off of a surface and come another direction. And I talked a bit about the philosophical side behind physics. How do I know you guys exist? Right? I mean, I can see you, but I mean, are we in the Matrix? Right? Like, so why do I perceive, he's wearing the same hat even. Why do I perceive Darian's hat? Broncos hat. I think he should know better. He wants to get a good mark. He should wear a Patriots hat. Anyways. Okay, so why do I see Darian's hat? Well, light is bouncing from any sort of light source. Let's just say these lights right here, right? And it's bouncing off his hat. Now, is his hat a shiny, smooth surface? So is it going to, what sort of reflection does it undergo? Nice, diffuse reflection, right? Diffuse is a word that we'd use to describe that it's going to bounce in all directions, right? Which means that some of the light bouncing off of his hat bounces towards me so I can perceive it. But not just towards me. It's not focused towards me. It also bounces towards you and you and you, which is why all of you guys can perceive Darian as well. Right? You can all see him. Right? If you were to have, say, a mirror, you guys have probably seen this before, this sort of illusion where you have like a light beam bounces off a mirror and it focuses on one little wall, and maybe it's like a laser and the cat happens to be like pawing at it and chases the laser around the room. You ever seen those sort of videos? Right? I mean, if it was off of a surface that maybe focused the light, then all of that light might go into just one spot. But, I mean, most of our everyday stuff, it's just going to diffusely reflect light. Sound good? Now, I showed you guys some work with mirrors the other day, and I didn't bother grabbing them out just yet, but maybe I can draw them a little bit on the on just a blank slide here. This is the idea I wanted you guys to be able to understand, the idea of a virtual image in a mirror. Let's say that we were standing right here, and there was an object. I'll just draw an arrow as an object right now. And that object was getting reflected in a mirror. Right? And so this would be reflected, and then maybe what you'd actually end up perceiving is you think that the image is right here. You guys get what I'm talking about here? Here's the actual object. And I'm going to perceive that the image is on the other side of the mirror. And like for this person right here, I will see it sitting right there. But really, if there's a person standing over here, really what's happening is he's going to perceive this image to be back there. But really what's happened is light has bounced off of the mirror towards this guy's eyes. But he feels and sees the image right there. And it doesn't matter where you stand. If there's a person standing over here, he would again perceive that same image to have been from right there, but really light bounced off the mirror towards his eyes. And so to me, I feel like this is the best way of describing a virtual image. The idea that all of us, regardless of where you stand, we're all perceiving that light source or that image source to have been in the same place behind the mirror. Does that work? Okay. Then we learned about three main types of curved mirror examples based on two mirrors. Let's see. These are really basic. If you approach light from this perspective right here, what kind of mirror is this? Convex. And this would be a diverging lens because it would cause your light to diverge outwards. Right? Whereas this one right here is concave, meaning all of your light converges on the same spot. Right? Familiar with this? Okay. Right, and the idea behind these converging and convex is that they can either create real or virtual images depending on the scenario. And maybe this slide right here is the best one to kind of re-illustrate this concept. This is one right here where the actual candle was right here, but in the sort of lens, it made it appear upside down. Here, the actual candle is right here, and it actually made it appear right side up and much enlarged. And then here, it is right side up, but it's actually pushed further back. And hopefully you're able to do kind of the math and do the two equations to figure out whether it's there were, what, 4 categories I need you to know? Virtual and real, enlarged or diminished, upright or inverted, and distance. You should be able to figure out whether the distance has either increased or decreased. Right? And so that's where the math formulas came in. Okay. Do you guys recall those basic concepts? Okay, so let's move forward then with a new topic then. Let's talk now about refraction and kind of build on this. Okay. The way I designed this unit is basically day 1 was kind of an intro day, and then topics 2, 3, and 4 are all different things that light and EMR can do. They can reflect and bounce, they can refract and bend, and then tomorrow you guys will watch my video on how they can diffract. Diffract means that they can actually go around objects. They can actually like bend around a corner. But I'll focus on that tomorrow in the video. So here's refraction. Basically, I like this picture to start with. You guys have all seen this optical illusion at some point in your lives? The idea that like as you see the straw, it clearly is not in one continuous line because light is refracting. And so actually in this glass, we actually see 3 different things where light's passing through. Light has to pass through the air. It also has to actually pass through the glass itself and then through the water. So I want to show you the 2 different boundaries. Right here to here, if you can see my purple line there, we can actually see the difference between the straw, and we're seeing the light waves bounce off the straw and to us through air. And then right here, it's then going through the glass. You see how there's that bend to it? But then there's actually another boundary right here. Here, it's between the glass and then the water, and that one was even more pronounced. This one just had a little bit of a bend. This one, like, there's actually like a gap there. And then I want to use this this big word that I put there. It looks bent, but I think we all intuitively know that that straw was not. Right? Where would a profession be that you'd actually like utilize this? Who uses this sort of stuff? Magicians. Right? Magicians use optical illusions to try to fool your brain into thinking something is not real. Right? But I want to try to explain how this works then. So here's one of many, many slides I have to try to illustrate this concept. And of course my board died. As soon as I got going. There we go. Okay. So here's how this basically works. Your eyes believe that the pen is right here. Your eyes think that the back end of the pencil is right here. However, the back end of the pencil is actually right here. Because here's what's happened. Light has come off of the back of the pencil, and then it's hit the boundary. And at a boundary between 2 different mediums, do you guys know the word medium? Like the stuff that stuff goes through? Wow, that was technical. The stuff that stuff goes through is a medium. Right? As it changes from the water medium into the air medium, it actually has the ability to bend, refract. And so your eyes think that it came in a straight line. And so you perceive it to be over here. In a way, this is like a virtual image. You think your brain perceives the back end of the pencil to be right here. But it's not. It was actually right here. And I like this photo to help kind of illustrate the same concept. If you were to be like a spear fisher and you were trying to like spear a fish and try to catch it in the water. I don't know if any of you ever tried to do this before. You're just catching a fish underwater. You actually have to compensate because your brain believes the fish is right here. And so if you aim the stick and try to spear that location right there, that makes all the sense in the world to your brain, except that's not where the fish is. Right? The fish is actually right here. Light waves have bounced off the fish, bent at the what would you call that, where the two medium meet each other, but your brain thinks that it was from a straight line, and so you aim right here. Does that concept make sense to you guys? You guys have all like experienced at some point in your life the idea of the optical illusion? So let's focus on some more then. More pictures of the exact same stuff, but maybe I made my point, so let's move on. Okay, scientists. We've actually known about refraction for a long time. I mean, this is something that back in the time of like Aristotle and Ptolemy and Archimedes, they would have known about refraction, right? I mean, it was pretty obvious that when you try to go reach in with your hands, try to catch that fish, why is the fish not there, right? Like they've known about this. But it wasn't until literally the year 1600, like right on the dot, 1600, that a scientist named Snell came up with the math for this. So add this guy to the list of scientists I need you to be aware of and his contributions. So Snell, this is Snell's law. And this one should be in your formula sheet, correct? Is this one, you guys have your formula sheets out in front of you? See if you can find this one here. Now, the best example of this law that I can kind of relate to is the sine law. Do you guys remember the sine law? Where there's like sine A over A equals sine B over B equals sine C over C? Where there's like 3 parts to it and they're all equal to each other? Well, this is a 4-part equation. So you don't actually have to use all of these values. You only ever use like a few of them at a time. So if you know about angles and wavelengths, use angles and wavelengths together. Or if you know about velocities and wavelengths, put them together. Okay? But like you don't need to know every single piece of information to use this. You only ever need to know about like say 2 of them. And the 1s and the 2s basically refer to either side of the medium. So like if you are going from water into air, then like water can be side 1 and air can be side 2 as these things kind of bend. Does that work? So here's the things you can use. You can talk about the angle. You can talk about the wavelength. You can talk about the velocity. Or N. N is known as an index of refraction. I like to think of this as like a coefficient of friction. You guys remember how coefficients of frictions were just this like unitless number that helped you, I don't know, solve a question? That's kind of like this. It's like a leading coefficient. These are like leading coefficients. They don't actually have units to them, but the larger the number, the more that it refracts. The smaller the number, the less that it refracts, basically. So, turned off again. Come on, stay on. There you go. Okay, so like here's my notes on the index of refraction. It's the way of comparing what's known as the optical density. This is probably the best way of working with it. The larger the value, the more dense the material. So one of the least dense mediums that we can have an EMR wave go through would be air. Right? Really, air. There's stuff in air, right? There's nitrogen molecules and oxygen molecules, but it really doesn't get in the way all that much. Whereas if you were to try to run an EMR whatever wave through water, water is a whole lot more dense. But there's even more stuff more dense than water. I've got a table here. Like diamond, for example, is one of the most dense things that you can run things through. It's actually one of the reasons why diamonds kind of gleam, is that as light waves try to hit diamond, they don't actually necessarily bounce through them all that well. They actually reflect back towards you again, which is why you can kind of see them like glitter and shine and sheen and stuff like that. So anyways, these are a whole bunch of N values. Sorry, I'm going to have to stand over here. This thing's not staying connected. Stay on. Boo. This stinks. Okay, give me 1 second. I'm going to go plug it in and hardwire it in today. have to do this a long way. Okay. Oops. You guys still good so far? Okay. Okay, so maybe here's the last thing. I already talked about this, but make sure that you're clear on this. Units of refraction for like these index of refraction, no units. Okay. Sine, the angle itself is going to get measured in degrees. Wavelength is going to get measured in meters, and velocity in meters per second. But this guy right here, no units. So I'll show you how to use this formula in a little bit, but maybe more importantly than using the formula, we should talk about the theory behind how far some of these things actually will refract. So here's my first example here. Let's say you have a beam of light traveling in glycerin, and then it hits the boundary of water at an angle of 43 degrees with the normal. I want to talk about this phrase here, with the normal. Do you guys know what that means? Okay, what's normal force? It opposes, well, it doesn't necessarily have to oppose gravity. What if you're on an inclined plane? That's not always true. Normal forces are always perpendicular to the surface that they're on. So maybe this phrase right here, with the normal, means that if you were to have a boundary right here, the normal line would be drawing a 90-degree line right here. This is known as the normal. I have no idea why we chose that word. Looked it up, I guess. But a perpendicular line would be the normal. So why don't I say that this right here is glycerin. Glycerin. And we're going to have it travel from glycerin into water. So it's actually going to give me the angle. It says that it's coming in at 43 degrees with the normal. So I'll have the light come this way, going from the glycerin towards the water. And then the angle of 43 degrees with the normal means that this angle right here is your 43 degrees. Not the angle right here between that and the water, but the normal is the perpendicular line. Does that terminology make sense to you guys? Okay, well, there's two possibilities here. Let me draw them out. Don't draw this part here because I'm going to erase this in just a second. Here's one possibility. What could happen is the light could bend like that, and it could become even more steep. That's one possibility. The other possibility is that light could bend maybe this way and bend like more towards the surface. You know what I'm saying here? Those are the two possibilities. We need to be able to figure out which one it's going to be. And you could do this if I give you numbers, but you also could be asked theory questions involving this as well. So let's do it with the math first, though. We'll figure out which one is which. According to our formula, N2 over N1 should equal sine of theta 1 over sine of theta 2. I'm just snagging just a little snippet of that formula. By the way, quick thought here. Sine, wavelength, and velocity all have the 1 values on top. The indexes of refraction, they flip and they put the 2 value on top. So that's why it's 2 over 1 here. No, so then, good question here. It doesn't matter which one goes where, but be consistent. So the advice I give kids when they solve a question like this is literally in your diagram, just literally pick which one to be 1 and 2. So arbitrarily, glycerin is 1, water is 2. Done. Right? You could flip it around for all I care. Just make sure that you're consistent. Right? So like write it directly on there so you know which one's 1 and 2. And then like start plugging it in. So N2 would be the N for water, which is 1.33. N1 is for glycerin, which is 1.47. Sine of theta 1. Let's see, the sine would be 43 degrees. And then for theta 2, we don't know that one. So now really it's just a math problem. Well, no, it does because the 43 degrees is the angle of the glycerin in one, so it definitely has to go there. Because what we're looking for is the angle again with a normal right here. We're either looking for this little small angle right here, or we're looking for that angle around to there. You got to continue with one always being above the medium. You can't just you can't change it halfway through. Do you guys algebraically know how to rearrange this thing? I don't need to do a huge lesson on that. No one's saying anything, so it's either Monday morning or you're good. One of the two. Nice. Sine of 43. Make sure you're in degrees, by the way, not in radians. I got 48.9. You got that as well? Okay, so let's go back to our original example here. I drew two possibilities of this angle. I'm now going to continue that normal on the other side of the boundary. So I'm going to draw this perpendicular line right here. Now, if this guy right here was 43 degrees, I now need it to be 49 degrees. So it's going to have bent which way? More like this way. It's going to bend that way. So that if this was 43 right here, now this angle right here is now larger. It's now 49 degrees. It's kind of bounced outwards, if that makes sense. So one of the things I need you guys to be able to do is use this formula, but I also need you to understand the theory behind it, which I'm going to have written out on this slide right here. If light goes from something that's more dense to less dense, it bends away. And if it goes from less dense to more dense, it bends towards. Let me go back to this. I know you guys are on this slide right here. Stay there. I'm going to flip back, okay? We were going from glycerin to water. Glycerin was 1.36, and water was 1.33. We were going from something more dense to less dense. You guys in agreement on this? We were going from a more dense material in glycerin to a less dense material in water. So based on that, from more dense to less dense, it will bend away. Is that what happened? Yeah, it bent away, right? This is where my normal was, and this bent further away from where it was. Or if you were to use this diagram right here, let's pretend this is going from air into water. Here we're going from something less dense, because air is not very dense at all, right? To water. Water is clearly more dense than air is, right? And can you guys see how it used to be this much angle right here? I don't know, let's call that 45. Well, now it's bent, like it's been pushed in more. So, I don't really want to write this down on your formula sheets, which you'll eventually have taken away from you, but it's not a bad idea to have written down just so that you know the theory. So, here's how I try to remember it. Here's how I try to remember it. When light is going from air into water, it wants to try to find the shortest path it can. Imagine that the water just all of a sudden it ended right here. Let's say that it tried to keep going on the same line that it was going like this. You see how this distance right here is, I mean, if I had a ruler, it would be, let me even try this here, line tool. If it just continued on the straight path, it would have to go that distance right there. But if you were to bend it slightly and bend it like this, do you see how the distance it had to travel was shorter? Well, if you were light, imagine that we're the magic school bus and Miss Frizzle shrivels you down to the size of a photon. Poor choice of word. Miss Frizzle shrinks you down to the size of a proton. Okay, photon, not proton, photon. And you had to choose between going through this really dense, thick water. If you had to travel going here, it would end up being a long distance to travel, right? But if you could bend, you would bend so that you traveled to like here. Well, now you're not traveling quite as far. Isn't that logical? That when you travel through a thicker material, you'd want to find the shortest path. Understand what I'm saying here? Right. If this were you and you had to wade through like a bog of mud, right? And here's the sidewalk, and it's nice and clean, and this is mud right here, right? And you were planning on traveling in a nice straight line. That's what you're planning on doing, right? But then once you get to this location right here, you recognize, wow, look how far I have to travel. Look how far I have to travel through this mud. Wouldn't it be smarter to maybe like cut your travel distance a little bit in half so that you only have to go from here to get out of the mud rather than from here to get out of the mud? So that's how I keep it straight in my mind, if any of that made sense to you, is that when you go into a thicker material, you bend towards the normal because that's going to be your fastest path out. There might not actually be an out, but if the medium eventually stopped, if this water was like contained here, this would be the fastest way out. In theory, the very, very fastest way out would be to bend completely to the normal. But not everything can bend quite that far. All right, let me move on. Here's an example of a prism then that has the ability then to bend light, but it actually bends it twice. Look at this. As the light comes from the air into the medium here, clearly you guys can see that it bends, right? Let's draw a normal line. Where would that normal line go on this picture? Perpendicular to the boundary. So if the boundary was right here, perpendicular to it would be like that. You know what I'm saying there? Like I'm drawing like a crosshairs. It's just it's kind of tilted because the picture's tilted, right? Now, I don't know the exact angles, but I could probably estimate that this angle right here, why don't I call that, say, 30 degrees? I don't know that it actually is 30 degrees, but let's pretend it's 30. Do you see how this angle right here on the other side is clearly less? Like this angle right here might now be, say, 20 degrees with how it bent, right? Because light tried to find the fastest way through. Now, let's say the light wanted to go straight. I'll use my line tool one more time here. If the light wanted to continue going straight, see how much distance it has to cover to get out of the prism? But by bending, the light managed to find a shorter path, and so rather than having to travel this much distance, it only had to travel this much distance, and it found a shorter path out of the boundary. But that's not the only thing we can glean from this, because we have a second boundary we can focus on as well. Again, it traveled again from this glass into air. Well, what should happen as it travels from a thicker medium into a thinner medium? Rather than bouncing towards the normal, it should now bounce away from the normal, right? And so this angle right here of 20 degrees has now bounced back out to this angle here of, say, 30 degrees. Here's a really cool thing. This line right here and this line right here, parallel. Which kind of makes sense, shouldn't it? Right? As it bounces in to a new angle, it should bounce right back out at the other same angle. Wait, let's try another math example. You have light traveling a speed of 2.21 times 10 to the 8th in an unknown medium. Let's figure out what this medium is. So it may feel like we don't have enough information here, because I literally gave you one number. And that's actually the point behind this example I'm making here, is that as you look at it, you go, Chris, I don't have enough info here. But that's not true. There's hidden information here. It was traveling a speed of light in an unknown medium, but we do know another speed of light in another medium. Air, yeah. So even though I don't know what the unknown medium is, so like let's say that we have the n of the unknown guy, we know the velocity of the unknown guy is 2.21 times 10 to the 8. I do know the n for air. It's on the previous table, by the way, and you should memorize it. Air is 1.0003. Essentially, it's 1. 1 being like a vacuum. If there was literally nothing for it to travel through, material-wise, and it went through a vacuum, it would be 1 right off the bat. Air is 1.0003. But then we also know the speed of light in air, because the speed of light, if we don't slow it down, is 3 times 10 to the 8. Do you guys see how we actually do have enough information to solve this question? It didn't appear like we did, but we do. So, velocity 1 over velocity 2 equals n2 over n1. I just got to pick one of them to be 2 and one of them to be 1 and just stick with it. So why don't we make the unknown stuff the 1s? And let's let air be the 2s. So hopefully you can get to this point where you're plugging in values. Can I show you a quick little trick? I shouldn't ask, can I show? I'm going to show you a quick little trick. See how this is times 10 to the 8 and this is times 10 to the 8? You could cancel that if you wanted. Right? Because you have a times 10 to the 8 on the top and bottom of the fraction. You may as well cancel them both. So essentially you have to take 2.21, divide by 3, and then times by 1.0003. And that should get you your N2. Yeah. Did I screw that up? Yeah, it should be. Good catch. Thanks, Michael. Good catch. This is a good learning moment. Okay, so it's N2. N2 is air. You're right. I totally goofed that up. And N1 is the one we're looking for. Okay, so 1.0003 times 3 divided by 2.21. I got 1.357. All right, let's go back to that table on the previous slide then. 1.357 is ethanol. There you go. Wait, now this table, by the way, is not something I expect you to memorize. I would like you guys, though, to know air. Okay? Just in case that somehow on the diploma they just expect that you know what air happens to be. Okay? But otherwise, N values, either they will give you an N value or they're asking you to solve for the N value. But you should know what air is. So maybe write that down on your formula sheet somewhere. The index of refraction for air, 1.0003. 1. Okay. Does it say in a vacuum? It just of air. Okay. I believe on my assignments and stuff, I used 1.0003. But for that one there, then hopefully that extra like 0003 doesn't really impact it all that much. Right? But does it logically make sense, though, that a vacuum itself, literally nothing, should be a value of 1? And then that air is essentially, I mean, compared to my water bottle or something like that, air is almost nothing for resistance. Right? But hopefully you'd agree that there should be like a little bit of resistance added to it. So try to use the 1.003 numbers in my assignments. Okay, let's try another one here. You guys have heard of prisms before, I'm sure, right? The idea of how you can send light into a prism and it refracts it out and causes it to show like a rainbow. Okay. Let's talk about the math behind how that works then. Let's say that you had some red wavelengths. Okay. Let's say you had red light and you shot it through, like, say, some sort of prism. Only maybe it's not necessarily a prism, but it functions the same way. You're going to shoot it from air into a flint glass. Let's figure out what sort of wavelength the color would be inside the glass, because it's going to actually change. So, I mean, even let's just draw a picture here. You have red light coming in, and then it's going to bounce another way. I don't know what it's going to turn into. On this side right here, it's air, and on this side right here, it's flint glass. Okay, air, you can be 1. Flint glass, you can be 2. Just start using your formula. So it's what? N2 over N1 will equal wavelength 1 over wavelength 2. Okay, N2, flint glass, was the 1.75. Air, I know your formula sheet says 1.00. Let's just go with the 1.0003, though. Just add on that extra little bit. Oops, didn't want that. And then wavelength 1, it was red light when it went in. Red light is 700 nanometers. Let's solve for wavelength 2. Okay, first question a kid might ask me, do I have to convert this nanometers into meters? The answer is no. Because if you just solve for wavelength 2, the unit of wavelength 2 would also be in nanometers. So you don't have to take the time to bother converting it times 10 to the minus 9. You can just use it as is. Okay, rearrange. Ooh, 700 times by 1.0003, divide by 1.75. I got 400 basically. You guys able to get 400? Okay. So this could be a way they test it on the diploma then. I've seen this one on one test at one point. It didn't ask you what the wavelength was. It asked you what color it would be. Isn't that mean? They give you the math question, but then they don't, the 4 multiple choice answers aren't that. It's basically, is it red? Like, let's say the 4 answers were orange, yellow, green, or purple. Orange, yellow, green, or purple. Which one do you think this is going to be for color? Probably purple, right? Because the wavelength of red is about 700, 750 maybe. Purple is 350 to 400 or so. I think my very, very first slide in the entire set of notes actually has the spectrum on there. So you should know roughly where it is on the spectrum. Oh, goodness, how many notes do I give you guys? A lot of notes. There you go. So red is in the 700 nanometers, and like blue, purple is in the 400 nanometers. So, I mean, then kind of to start logically working backwards, right? So then kind of the very, very middle of that at 350, 500 or so, 400 or so is going to be your green. So yellow and orange are the 600 range. Blue is your 500 range. Okay. But they could assess you that way, and I have seen one before on that. All right, you guys have any questions so far? Okay. Okay, I've got 2 last things I need to cover in my last half hour. I'm going to talk about some applications of how refraction works on the next slides, but I'd like to show you a quick YouTube video. And this one should be on my website. So, Brady, I don't know how well this will play over the VC streaming thing, but if not, I'll find you the video so you can watch it later. Here's the deal. I would love to pull out some lenses and kind of literally show you guys this hands-on. I don't actually have any really good lenses to try to do refraction with, but this guy did a really awesome YouTube video, so I think it's just easier for me to show you his video rather than try to do a lab myself.
Let's get to work. Here's a mirror, plain mirror, and here's a beam of light coming in. And you see that as the beam of light comes in, it's going to leave at the same angle as it enters all the time. And the interesting thing about mirrors is that we can bend them. So I could start with a mirror like this. This mirror is concave over here. So as I come in parallel to the axis of the mirror, I leave, always sort of aiming at a certain point. Do you see this point where it's always kind of hitting? I might call that the focal point of the mirror. Sorry, I'm kind of blocking it right there. Yeah, there we go. Right there. All these parallel rays are converging right there. That defines a focus of the mirror. So this kind of a mirror, a concave mirror, is a converging mirror because it causes the rays from wherever they start, here, to converge at that single point. But if I flip this mirror over, notice I've got a mirrored surface over there. I got a diverging mirror now. Check it out. See, it causes the ray to go up, and down here the ray goes down. Yeah, this is getting really hot. Wow. Yeah, good. So that's a diverging mirror because it's convex. And we also have discussed the principles of refraction. So as I send a ray of light into here, if I send it straight in, then you see the ray of light inside the block, and you see it come out of the block and everything's fine. But if I send it in at an angle...
Awesome. Let's look at this thing right here. I don't have a normal line drawn on here, but imagine there's a normal line kind of... Actually, I can draw it on the whiteboard. It won't show up on the notes afterwards, but can you guys see how this angle right here, let's call that, I don't know, 45 degrees. Right. How does that affect this new angle right here that's later? I don't know, maybe 30 degrees. See how it's smaller? What does that tell us about that material? Is it more thick or less thick, dense than air? More dense, which, I mean, pretty much everything is more dense than air, but does that fit together? Okay, I'll keep going here.
If I send it in an angle, let me put a block like this. That's probably more interesting. If I put the block like this and I send it in at an angle, you see that I can get the ray of light to come in at a weird angle, and then see it breaks here. It's not breaking like it's broken, but it's definitely making a very sharp bend, and it goes this direction and then comes back out. And notice this initial ray coming in is parallel to that final ray that's leaving right there. But in the medium, it's going more slowly, so it tries to actually minimize its time in the medium.
I want to focus on that thing that he says there. It has to go slower, right? I mean, think of it as a resistance, right? If you were able to walk a certain speed in air, and then I asked you to try to walk through a swimming pool, you wouldn't be able to walk as fast, right? Because it would slow you down. Well, same thing with light. Light is trying to travel through air, no problem. Easy peasy for light to go through air, right? No resistance. But make light try to go through this block of acrylic, and it's getting slowed down, right? So what does it try to do? It tries to find the path of least resistance, which is why it bends and tries to shorten its path. Rather than try, sorry if I'm being redundant here, but rather than try to go all this long way through the acrylic, that's a long distance to travel, right? What it does instead is it bends and tries to find a shorter distance out. Okay, that is such an important concept that I really need to be repetitive today.
Principle of least time is a hugely important physical principle. So the light knows which way. I mean, I guess it tests every way in some very interesting way. And it tests every possible path and finds the path that takes the least time and takes it. So knowing this, you guys could actually just pause your screen and find the index of refraction of this block of plastic that I've got right here. That's cool. But notice that the incoming ray is always parallel to the outgoing ray. Yep. But what if I have something a little more interesting, like a curved block of plastic or glass, or a really curved block of plastic or glass? Notice this. I bring it in, and it curves really dramatically. A parallel ray coming in seems to be always pointing towards something. Watch this. This is convex, right? Wouldn't you agree this is convex? Now, I'm saying that everywhere in here, we're kind of pointing towards a particular location. Problem is, this is a circular cross-section, so it doesn't have a really well-defined focus. But I'm going to argue that somewhere around here, all the parallel rays are trying to join, and this must be a focal point. So there's a focal length that we can define for this very strange lens. With a more reasonable type of lens, we'd do it like this, and we'd say that is, oh, look at the focus on this guy. I'm bringing in parallel rays, and the focus on this guy is probably much further away. It may even be beyond my piece of paper. As the rays come in parallel, they bend more and more as we get further and further. Well, we get closer to this side of the mirror, where the angle is sharper. Ultimately, might make sense to look at a prism. Oh, a prism has all kinds of cool things we could study. Notice that as the light comes in, it bends towards the normal as it enters the prism, and it bends away from the normal as it leaves the prism. So you get all.
Okay, let's revisit that concept again here. This is not a square block now, right? Right. The previous ones I've given you a square. This triangle is a bit different. So if I were to try to draw this a little bit, let's just make sure the lines make sense. So here's kind of our normal. As this light is coming in, it bent like this. This angle right here, hopefully you'd agree, much bigger than the other angle, right? So it makes sense it bent towards the normal, thicker material. But there's a second boundary, right? And the second boundary was right here. Now, this one's nowhere near as good, just because like you see how the light ray is almost coming in just absolutely perfect anyways, but you can see how it bends a little bit again a second time, right? You know what I'm saying there? And so here it bent towards the normal. Here it should hopefully be bending away from the normal. So if I were to draw kind of a normal line right here, this angle right here might be, say, like 5 degrees. This outgoing angle right here hopefully might be like, say, 10 degrees. Right? The angle should enlarge on the way out. So, I need an actual eraser here.
Kinds of cool stuff like this, bending towards the normal, bending away from the normal. Ooh, that's kind of ideal. It's bending towards the normal Watch this though. See all this light that's coming out right here? As I get this more and more dramatically bending away from the normal, see it's really coming into this intersection here, going into this smaller index of refraction. Light can travel faster out here, so it wants to spend more time out here than it does inside the block of acrylic. Watch as I go even steeper. Can you notice what's happening right there? That light is getting closer and closer to never making it out of the block of plastic at all. Watch it. Watch it now. Careful. Careful. Ooh, you see that rainbow effect? Yeah, that's why they call them prisms. Look at this. Oh! Suddenly, no light at all escapes. Now the light is entirely trapped in there. That's called the critical angle right there. Boom! That's the critical angle. You could measure that. It depends on the index of refraction. In fact, it's a very easy bit of math. Maybe you'll make a video to do it, or maybe you'll do it on your own for crying out loud. And then, once it's totally
So excited, hey?
reflecting, then we get a bounce off of here, inside here. Look at that. Look at that. You see that other beam is also totally internally reflecting? And I've actually got no light at all out here. No light at all is coming off of this bounce. But if I go really close, I can get the light to quantum jump through there, which is really interesting. I don't want to talk too much about quantum physics with you right now, but notice that I can make total internal reflection happen right here. Finally, we can also make a lens that's shaped like this. And the funny thing about this lens is I bring a ray of light in that's parallel, and it's it's not bending at all if I'm in the middle, right? But it bends down at the bottom, and it bends up at the top. So this kind of a lens is diverging, but it's concave. Remember our converging lens? The converging lens is convex. Whoa! What if I put these two together? Check this out. Now, a ray coming in parallel leaves parallel, but it's doing all kinds of funky stuff in the middle. Yep, I agree. Bringing two lenses together makes some very complicated optics happen, which is really fun. But note right now that the action of a mirror is the opposite action of a lens. They're sort of like capacitors and resistors, or capacitors and inductors in that sense, because a concave lens is diverging, and a convex mirror is diverging. And similarly, a concave mirror is converging. See that focal point that's forming right there? And a convex lens is converging. Okay, bye.
I love the way he ends that. Fascinating. I don't know whoever made that video. Okay, I would love to show you more stuff in person, but I don't actually have the materials to do the optics. So that video there, I felt, did a pretty good job of showing you some of the concepts. You guys have any questions on that so far? Okay, well, with that, then let's talk about a couple of main applications, because we need to, physics, this should get used somewhere. To me, the most common place that you'll think of where lenses refract, optometry. Right? For any of you guys who are wearing glasses, that's essentially what's happening, right? Is you've got some sort of lenses. Light is being asked to bend through those lenses at different angles, ideally making it so that it hits your eye and your retina in a more ideal location, right? And so I'm going to focus on, for these last few minutes here, some of the applications we have. So before I get to actual optometry stuff, let's talk about these. This application he actually mentioned, the idea of total internal reflection. You could actually make it happen where, as you have a boundary between two objects, if you tilt back the angle enough, you can actually make it so that light never actually leaves the object in question. You guys ever heard of fiber optic cables? Fiber optic cables actually work on the idea of total internal reflection. Basically, you don't lose a signal strength because the signal always just bounces within inside the cable through this sort of reflection concept. What I need for you guys to know is the angle math. Right here would be, say, theta 1. What is theta 2? This is a hard question. Let me do a different one right here. You guys see how right here, this is theta 1. Right here is theta 2, right? Right here would, say, be theta 1. And right here would be theta 2. If you're going to have total internal reflection, what is the second angle? Say it louder. What is the second angle? You got it, 90. Yeah. So if we ever talk about total internal reflection, it's going to feel like you don't have enough information, but you do, because the second angle is 90 degrees, right? Because then what ends up happening is this angle right here, as the light comes in, rather than bouncing out of the surface, it actually either remains along the edge of the surface or it bounces back inwards. Okay. So this angle right here has a name. We call it a critical angle. And I think it's on my next slide, so I won't bother spelling it out. But the critical angle, there it is the angle at which the beam does not leave the object anymore and just skims along the surface. Meaning that your theta 2, your second angle here, is 90 degrees. That's what causes total internal reflection. So I actually did the math on this one earlier. I'd like to prove it again now. The critical angle for water to air is about 48.8 degrees, meaning that if you have water to air and you up this angle right here, like if you were underwater and you shone a flashlight, that light would not exit the water itself. It would actually bounce around and bounce back inside water. Let's try to prove this that it's 48.8. Doesn't it feel like you have like no information here? But we do. Oh, that's not a straight line at all. Let's try that again. I'll use this as my straight line. Let's say that this is water down here. Let's say this is air right here. And what I want to do is I want to have it so that the angle of my light from water to air is so steep that it doesn't come out the other side, but that it just like kind of runs parallel to the surface. What we're going to look for is this angle right here. I know I told you that it's 48.8, but I want to prove that it's 48.8. So let's look for this angle right here. But good news is we know that this angle right here, theta 2, we know that that's 90 degrees. And then water and air, we should be able to figure out their n values, right? Because air has an n value of 1.0003, and water has an n value of, I think it's 1.33. Yeah, 1.33. So, whose law do we have to use? Snell. When did he discover it? 1600 on the dot. You should know that sort of stuff, just in case it comes up. Okay, so n2 over n1 equals sine of theta 1 over sine of theta 2. Okay, I made air be 2, so that's 1.0003. And 1 I made water, so 1.33. Theta 1 I'm going to look for. We know that it's going to be 48 degrees when we're done, but I just want to prove it. And then theta 2, this is the important one, that's going to be 90. If you're trying to find a critical angle, your second angle is always 90. So take 1.0003, divide by 1.33, times by the sine of 90, inverse sine, 48.8. So that is your critical angle. You follow that? Okay, so there's one application, finding a critical angle where light literally bends so much that it doesn't even leave the medium you're talking about. Here's another application. I don't have any math behind this one, but you should know about prisms. Isaac Newton actually did a lot of work with prisms, and I believe he's the one who coined these terms. So the two terms I need you guys to know are dispersion and recomposition. And honestly, I think these words are intuitive. I probably hardly even need to talk about this, right? Here's a prism, and white light is going in. Do you guys know what white light is? All wavelengths of visible light. So it's like it's a smattering of red and yellow and purple and blue, right? White light is basically all of your main wavelengths kind of all collectively together. And if you put them all together, color theory says they look white. Okay. So if you bring in white light, then if you send it through a prism, what ends up happening is since they each have a slightly different wavelength, they diffract a different amount. and so it causes them to spread out a little bit. So this hopefully makes sense. This right here would be dispersion as they spread out into their different colors. Recomposition, though, would be with a second prism. You could actually recombine them all. We kind of saw that in the video. The guy kind of did that. He didn't really use a prism strong enough, like with enough of an index of refraction to actually make that white light look like different colors, but you guys have seen a prism before, right? If not, I do have a prism. We could probably try something. Wait, this is the most important section, though, the lenses. Similar to mirrors, we need to work on some different diagrams and use some math for focal lengths and diverging and converging lenses. So we got about 15 minutes left. I should get going on this here. To me, the application here is obvious. This is optometry, right? Anyone who wants to work with glasses works on this. So you've either got converging or diverging lenses. Here's what you guys need to know. This one right here, which is a double convex, is actually going to converge. And this one right here, which is a double concave, is going to diverge. Let me show you how. When you have a lens, you have to make one subtle adjustment. You actually have to draw a line right through the middle of the lens. Okay? You know how when we worked with mirrors, you draw a line and it would like bend when it touches the surface of the mirror? That's not what's going to happen with a lens. When you work with a lens, it does not bend until it hits the center. Okay, so you actually have to have a center axis through the middle. Okay. You also have two focal points because you need a focal point for like this curved section, but you also need a focal point for the other curved section. So you always have two focal points. And then the third thing here, you don't actually have a center. You know how a center was twice the focal length? We don't really have like a center out here. This is not where you'd put a center. We actually still will work with a center, but it's in a new location. Where? Yeah, like right in the middle, right where the center would logically be. Okay, so here's your rules. If it goes through the focus, it reflects parallel. If it goes parallel, it goes through the focus. And if it goes through the center, it does nothing. This is exactly like what we did before. Let me show you an example. Let's say that you had an object right here. Maybe just let me do this one first rather than you guys drawing along. Just let me do one first. Let's say that you had light that was going parallel. Parallel rays would then go through the focus. So far, so good? Let's say that it went through the focus. Okay, this is obviously, my lens isn't big enough. Pretend the lens was big enough. Okay, like, I didn't draw this large enough. Parallels would then go, sorry, if they went through the focus, it would come out parallel. Lastly, if it goes through the center, nothing happens whatsoever. Do you see all three of these things converged right here? Here's what's going to happen then. You are going to get an image that is going to be upside down and enlarged. And this is kind of how certain sorts of glasses work. Now, your glasses don't work this way. Your glasses actually don't use one of these converging lenses. They use diverging lenses. The projector, though, the projector actually uses a converging lens. Where, I mean, if we were to actually tear that thing apart, I showed you guys the mirror in there yesterday. This guy is actually going to be taking an image, and it shoots it through the lens, and it actually causes it to enlarge upside down, which is why sometimes you actually have to flip a projector the other way around because it makes it upside down images. This is actually known as a real image now. It's backwards, and this is where I find this so frustrating because real and virtual I struggle with. So on a mirror, a virtual image is behind the mirror. On a lens, if it goes through the lens, though, it's real, which kind of makes sense because shouldn't light actually pass through a lens? That seems logical. So the way this would work then is that like a projector, if you were to project off of this projector here, your light sources, if you were to put like your screen right over here, just like our whiteboard is right here, it would actually project it onto that screen right there. So you actually have to flip it around. If it goes through a lens, it's actually a real image. Let me try some more examples here. Actually, that was the example. Never mind. I didn't know that. Did you guys know that? Is that on the next slide? Okay, well, here's the picture of what I just drew, I guess. So let me talk through the properties. This would then cause the image to be enlarged, inverted, and real. Now, one of the cool things about this is that, let's say you were standing right here, and we put a screen right here. You would then see the projection on the screen. But if you were standing right here, you could also see the same projection on the screen. If you were standing right here, you could also see the same projection on the screen. Do you know what I'm saying here? So a real image, I struggle with this a lot. A real image then would be, could you all stand here and look at it and see it get projected? If that was the case, then it is real, because everything has converged into one spot. And so I don't care where you're standing. I can see this convergence right here. You can see this convergence right here. You can see this convergence right here as your image gets shone through the lens. You know what I'm saying here? So that's what defines something as a real image. Let's try another one. Why don't we do this one together? Okay, this is going to be a diverging lens. Cell phone? Still good? Okay, let's do the easiest one first. Anything that passes through the center goes undeflected. So I'm going to take a line from the top of my object, and I'm going to run it directly through the center and do literally nothing to it. Okay, then I'm going to run something through the focal point, and I'm going to run it right through up until that center axis and then stop there. What happens here? It went through the focal point. It should now go parallel. Okay, so then parallel should make it go like that. And if I run a ray that goes through, I messed up. Sorry, I messed up. I hope you guys didn't draw in pen. I need you to just go with the first line. I'm sorry, did I really bugger you guys up? Oh, I hope that helps here. This is a good learning moment here. I realized why I buggered this one up. You guys see how this is a concave lens right here? I bounced it through, I think, the far focal point, did I not? It's actually supposed to bounce back through its own focal point. Right? Because isn't that how like a concave one would work? Is that it would bounce back through its own focal point? So the parallel one bounces back through its own focal point. The one that I screwed up, sorry, we'll have to chat more later, Brady. I'll keep recording this till the end. Hopefully you can watch the last 5 minutes here. Here's where I screwed this one up. I actually have to aim. I have to aim at the far focal point, and then it's actually going to bounce it backwards that way. You see how they all converged right here at that crosshairs? Typical question from students is like, holy smokes, how am I supposed to know how to do this? Practice. The more you get used to it, the better you'll get at recognizing where they're all converging. Long story short, you're actually going to be seeing this image right here. I'll give you a second to kind of comprehend that. I'm going to erase it. I'll do it one more time, just so you get a chance to see it from the top here. Yeah, you got a science next door. Okay, so one more time here. On this lens here, the easiest line to draw for sure is the one right through the center. That one's not changing. Okay. Now, if I draw a line parallel, see how this is a concave side right here? It's going to cause this guy to go like this and oops, this and say like that. Then, if I were to aim at the far focal point, it'll actually cause it to bounce parallel, which would be there. Okay, you know how on the last example I did back here, see how they all converge at a single point? Are all of these rays right here converging on this side of the mirror at a single point? Yeah, would you mind? Thanks. Yeah, I'm not here tomorrow anyways. Tell them that later. Do you see how these guys are not converging at a single point? These are diverging, right? If you were to stand right here, would you see all of these rays kind of converge at a certain point? Like you did right here, where all of these rays converge at a certain point, so we could all watch the screen at the same time? No, this is a diverging mirror. So rather than seeing a real image, you would actually be able to see a virtual image, which would show up right here, and you would perceive it as though it was here. Let me go back to the start of my my lesson. Do you guys remember the fish? And how you thought the fish is here, but it's really there? This is how your glasses work. If you were right here, and you were looking at this object, and you were to look back through the lens at this object right here, you would think that it was right here. You know what I'm saying? But it's not right here. It's actually right here. Now, if you were to be right here, and you were to be looking for this object through the lens, it actually is right here, but you would think that it's right here because your line of sight would cause you to perceive it as being here. This guy right here. If you were to look through the lens, the actual object is right here, but where does his brain perceive it as coming from? Right there. You get how that works? And so this is actually now a virtual image. The fish itself, here's my fish, is over here. But if you're standing here, or here, or here, or anywhere in between, where do you all perceive the virtual fish as being? You perceive it as being here. So two different examples. In this one right here, do you see how light all converged all on the same point? It wouldn't matter where you were. If you were here, here, or here, we all see the light converging. That is us looking at the projector right now. The projector lens sent light through this lens, shone it on the screen, and I can see it here, and you can see it here, and you can see it here, and we can all see it here. And we're seeing what is known as a real image. Well, it depends on how the screen works, but yeah, I would say, right, if you put the screen this way, then we should be looking at it like this. Don't worry about you, focus about the object and the image. If the object is on one side and the image is on the other side, it's real. Okay. Whereas if the object is on this side and the image is also on this side, now it's virtual. And the best way I can describe this is that if you were standing over here or here or here, and you were looking through the lens, all of you would perceive the fish to be here. But it's not there. The fish is actually over here. Which is how your glasses work, right? They try to make it so that it refracts the light so that it tricks your brain into thinking it's in a new location and it focuses it for you. I'm definitely out of time. We're going to have to do this next part on Wednesday when I'm back again. But the last thing we got to do is work on the math behind this, because I've got some math word problems where we use the 1 over f equals 1 over do plus 1 over di. We can use that formula still. It still applies, only it applies to lenses. So why don't I end with this slide here? Here's your two main possibilities. If light goes through a converging lens, it can make an image. This is what our projector is doing. It is converging all of the light into one source. If there was a screen right here, like a movie screen, we can now all watch the same movie screen because light is converging. If I stand here, I see the same thing as you guys see from over there. Fair enough? However, with a diverging lens right here, see how the light is scattering in all sorts of different directions? Still useful, but a different perspective. If I look back through the lens, I would be looking at this object, but perceiving it here. You would be looking at this object, but perceiving it here. See how there's two different uses for them? This one is a real image. This one is virtual. Okay, I'll stop there. Sound good? It's tough stuff, eh? Like this is challenging. Okay, tomorrow I'll show you guys, or Kelsey will show you guys the video on diffraction, and then Wednesday we'll regroup and see how you guys are doing. Sound good? Okay. We'll talk to you guys later.